I am just out of the shower, so please excuse the wet hair. Okay, to wrap up our chapter on systems of linear equations in two variables, we are going to discuss the final topic, which is systems of linear inequalities, again in two variables. So we'll have two inequalities, two variables, and we'll have to find a way to graph those and get a solution. So a few definitions. So first of all, a linear inequality in two variables is any inequality of the form ax plus by, where a, b, and c are real numbers such that a and b are not both zero at the same time. We talked about that in the previous chapter. Okay, so that should be a review for you. Now, this is true for any of the four inequality symbols. So I could replace, basically you're taking a linear equation in two variables, but you're replacing the equals with less than, greater than, less than or equal, or greater than or equal. So you could replace any of the equal sign with any of those, and it would be a linear inequality in two variables. Okay. The solution to a linear inequality in two variables, x and y, is an ordered pair of real numbers such that when the x-coordinate and y-coordinate are substituted into the inequality for x and y, we obtain a true statement. Okay. So when we were dealing with these linear inequalities in the previous chapter, we had a situation where we have our Cartesian plane, okay? And we know that if we have some kind of a line in the Cartesian plane, well, let me finish my Cartesian plane. If we have some kind of line in the Cartesian plane like this red line splits this Cartesian plane into two regions called half planes. So this is a half plane and this is a half plane. We also found out that the actual line is kind of like the end point when we were talking about linear inequalities in one variable. So the line itself sort of became a boundary to that solution, and you either included that boundary line or not. So if you needed to include the actual points on the boundary line, we used a solid line. If you did not want to include the points on the boundary line, you used a dotted line. And that kind of told the reader, include the line, don't include the line. And then we shaded one of the two half planes. So the solution would be any of the ordered pairs that satisfy the inequality. So that would either be the points on the line or not, and then one of the two half planes. Okay. So the graph of a linear inequality in two variables is the set of all points whose coordinates satisfy the inequality. That's what I was just telling you about. So you have the points on the line, or maybe not, and then you have one of the two half planes. Okay. Now a half plane, remember, is the set of all points on one side of the line. Okay. So you have the line itself, it's a boundary. Above the line or on top of the line is one half plane, and under or below the line is another half plane. Okay, so the graph again is going to consist of one half plane and may or may not include the points on the actual line. Okay, so let's talk about how we're going to take what we learned back in the previous chapter about linear inequalities in two variables and merge that into this world of systems. Okay. So steps to graph a linear inequality in two variables. Okay, we've talked about this. You solve the inequality for y and then plot the y-intercept and apply the slope. We've already done this in a previous chapter. We're just reviewing it. You connect the points with a line. If you have a or equals to inequality, so if you have less than or equal, greater than or equal, that tells us that we want to include the points on the line. To tell the reader that, use a solid line. So you kind of have to go back to like way earlier in the course. We could have had something like x is less than -4, and we would graph that. We would find our end point, which was -4. We would use a square bracket or a rounded bracket. In this case, we would go rounded, and then we would shade to the left. So the solution was any value less than -4, not including exactly -4. We could have also had something like x is greater than or equal to 3. Well, you would graph by drawing a number line, locating your endpoint, and because we are going to include exactly 3, we would put a square bracket that tells the reader, hey, include exactly 3, the endpoint, and then you want to shade everything to the right of that. Well, now what's happening is we have this line that's acting kind of like that endpoint. We either want to include it or not. If we have an or equals to inequality, we use a solid line. If we have a strict inequality, just plain old less than or plain old greater than, we use a dashed line. That tells the reader you either include the line or you don't include the line. You then choose a point in one half plane to test. You substitute the coordinates for that ordered pair into the original inequality. If you get a true statement, you shade the half plane that contains that point. If you get a false statement, you shade the opposite half plane. Okay, so let's look at just two regular old linear inequalities. Okay, we'll eventually merge this with systems, I swear. So example 1 says, where'd my, there it goes. So example 1 says that we need to, I think I went too far. We need to graph the linear inequality. In part A, we have 7x minus 5y is less than 45. So I do want to solve this for y. This is standard form. We want to put it more in that like slope-intercept form. So I have 7x minus 5y is less than 45. I want to solve for y. I need to first move the 7x, so I would subtract it. When I subtract the 7x minus 7x is just 0, leaving me with negative 5y is less than negative 7x plus 45. I need to undo the multiplication of negative 5 and y. In order to do that, I have to divide all of the terms by negative 5 and be very careful. When you multiply or divide an entire inequality by a negative, all of your signs are going to change. And to compensate for that consistent sign change, you, the mathematician, have to reverse the direction of your inequality symbol. So we're going to divide everything by negative 5. That's going to leave me with just a y on the left. And that's going to flip my inequality symbol, making it now greater than. 7 divided by 5, we're not going to write it as a mixed number or a decimal. We're going to leave it as a simplified fraction, but we do want to take care of the signs. Negative 7 divided by negative 5 is positive 7/5 x. And then 45 divided by negative 5 is minus 9. So this is now an equivalent form of that original inequality. It's just solved for y. Now the slope is the coefficient of x, so we would say it's 7/5, and the y-intercept is negative 9. Okay, now we've seen this before, we're just reviewing it. Okay, so what I want to do first is plot the y-intercept. So that's negative 9. That could also be thought of as the ordered pair 0, negative 9. So at the origin, I don't go left or right, but I do go down 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I want to apply my slope. Since my slope is positive 7 over positive 5, I'm going to go up and to the right. So I'm going to go up 1, 2, 3, 4, 5, 6, 7. And then to the right, 1, 2, 3, 4, 5. Now, I could have also gone, that just made a heart. I don't know how that occurred, but it made like a little heart. Anyway, I could have also go down and then to the left, but that would have taken me off the screen. So I went up 7, to the right 5. I could do it again. I could go up 1, 2, 3, 4, 5, 6, 7, and then to the right 1, 2, 3, 4, 5. I want to know why that made a heart. I don't know what that was about. Anyway, we need to connect these points, but we want to kind of tap the brakes, slow down, and think about what we need to do, okay? So when you're graphing these inequalities, you either use a solid line or a dotted line. In this case, we have a strict inequality. That means we cannot include, it's not an or equals to, we cannot include the points on a line, on the line, so we want to connect with a dotted or a dashed line. And once we solve for y, we had y was greater than. That would tell us that we should be shading on top of the line, but we always want to test a point just to be safe. So let's go ahead and test the origin. I find it is easiest to test the origin because it's easy to plug in zeros. Okay, the only time you can't test the origin is if your line goes through the origin. Okay, so I'm going to test the origin, which is right here. I'm going to take my original inequality, plug in 0 for x and y. So I get 7 times 0 minus 5 times 0, and I need to know if that is less than 45. Well, 7 times 0 minus 5 times 0, that just becomes 0, and 0 is less than 45. This is true. So that tells me my test point, 0, 0, is part of the solution set, which tells me to shade on top of my line. Okay, let's try one more. So in this case, you got to be a little bit careful. We have 3x minus 5 is greater than or equal to 7. Notice we're missing a y, okay? So we have no y, which means we cannot cross the y-axis, so that means no y-axis. Well, it doesn't mean there's no y-axis. It just means we can't cross the y-axis. But there is an x, which means we have to cross the x-axis. Without a y, but having an x, the only way for that to happen is if we cross the x-axis but are parallel to the y-axis. That means this line is vertical. Okay? And anytime you have a situation where one of the two variables is missing, you want to solve for the variable that you do have. So we want to go ahead and solve for x here. So I'm going to start by adding 5. 5 minus 5 or negative 5 plus 5 is 0, leaving you with just 3x, and that is greater than or equal to 12. I want to divide both sides by 3. That'll undo the multiplication of 3 and x. 3 divided by itself is 1, leaving me with just x is greater than or equal to 4. Okay? Now, what I need to do is understand that this is a vertical line, and this right here is the x-intercept. So I'm going to cross the x-axis at 4. Now we have to ask ourselves, when we draw this vertical line, is it going to be dotted or is it going to be solid? In this case, we have that x is greater than or equal to 4, so we do want to put a solid line. And I'm going to do it in red just because I think when we do horizontal and vertical lines, it's sometimes hard to tell which is the axis and which is the line. That's what I do. So anyway, different color here. So let's see, from the origin, we want to go to the right. 1, 2, 3, 4. We're going to draw a dashed, nope, we're going to draw a solid line that goes through 4 on the x-axis. I'm not entirely sure what just happened with that. There must be some kind of programming that I clearly don't understand about this. Anyway, we've got 4. We're going to do a solid line. And then we have to determine which half plane. Are we going to shade to the left or to the right? Well, we're told that x is greater than 4, so that means we want to shade to the right of this vertical line. So that would be our solution. Okay, so make sure you practice just graphing linear inequalities in two variables, because it's going to be a huge part when we start talking about systems of linear equations or linear inequalities in two variables.